Okay, so our second section here, we're going to be looking at the inference about the difference between two population proportions. And remember, when we're dealing with proportions, we're always dealing with a z-test. So that makes things a little bit simpler for us. So as we go through this section, we're going to be looking at performing a hypothesis test for the difference between the two proportions using the p-value method. And then we're also going to do it using the critical value method. Then we're going to actually look at constructing a confidence interval for the difference of the two population proportions. So let's start out with just the hypothesis testing with the p-value method. Remember, this is the way if you're using the calculator really does help with the p-value method quite a bit. So we're going to look at an example here. In the year 2002, the General Social Survey asked 1,343 employed people between the ages of 18 and 50 whether they used a computer in their work. 916 said that they did. In the year 2008, they asked the same question of an independent sample. Now that's important. The samples have to be independent. So it might be the same population, but they're taking a completely new randomly chosen sample. This time they took a sample of 615 people, and 465 said that they used a computer at work. So what they're trying to test here is to see if that proportion of employees that use a computer at work has changed between 2002 and 2008. Now, if we had used the same people, that might put us in that matched sample or paired sample situation that we discussed earlier. Since it was a completely independent sample, then we're okay. So there are two populations involved, the population of all employed people at the time the survey was taken in 2002, and then the second population is the population of employed people at the time of the survey of 2008. Now, there's some overlap between these populations, but they are different populations. They have changed from 2002 to 2008, so we can consider it to be two independent populations. The question is whether the population proportion of people who used a computer in 2008 is greater than it was in 2002. So the way that's worded, it might hint at us what our hypotheses are going to be. Get to my pen here. So greater than 2002, 8 is greater than 2002. So what we're going to look at here is we're going to, they left me with P1 and P2. I'm going to label this as P8 and P2. So P2 is for 2002 and P8 is 2008. And so testing to see if it's greater than 2008 than it was in 2002, that's telling us about the alternative hypothesis, H1. It's saying that P2 is less than P8. In other words, it was greater in 2008 than it was in 2002. The null hypothesis always, if you recall, is that the two are equal. Now there's again that alternative way of writing it. One way of writing it would P2 minus P8 equals 0. That's one way of saying that they're equal, that the difference is 0. And if P2 is less, that means P2 minus P8 is negative or less than 0. Oops, I don't know why I put 8 there. That should be equals 0 here. There we go. So for this example, we have two independent samples, which is important. Now we do have to test our other qualifications as well. So they're going to use P1 and P2. P1 is going to represent 2002, P2 2008. P hat 1 and P hat 2 are the sample proportions. X1 and X2 are the number of individuals that answered yes in each sample. And 1 and N2 are the two sample sizes. So we need to examine the issue at hand and make sure it meets our qualifications. First, let's make our hypotheses. As I said, P1 equals P2 is the null hypothesis. There are at least three alternatives. Well, there are three alternatives for the alternative hypothesis. And notice we said that P1 is smaller than P2 because they're saying that P2, the 2008, is bigger than 2002. Okay, our test statistic. We're going to be testing the difference between the population proportions. So you'd have to find each population proportion. For this example, P1 is going to be the 916 over 1343. Now, notice I put the little hat over that saying that's the sample proportion. And p hat 2 is, let's see, where is it here? The 465 over 615. And I could just leave them like that. When I put them in my test statistic, I could just subtract them. But to find my standard deviation, I need those values. So I'm going to go ahead and divide those out quick. 9/6. Oops, come on. 9/16 divided by 13/43. Is that correct? Yep. 0.682. No, 0.682. And then 465 divided by 615. That is 756.756. So there should be a considerable difference there. So now we need to find our standard deviation. The standard deviation of the difference of the means. We're not talking about the standard deviation for a single mean. Remember, for a single mean, it's p times 1 minus p over n, and then it's square rooted. That's the standard error. Well, when there's two of them, we have to add those two together within the square root. So this is going to be the square root of 0.682 times 1 minus 0.682 is going to be 0.318. I just subtracted 1 minus the 0.682 over n1 is 1343 plus p2 0.756 times 1 minus the 0.756 is 0.244. That's going to be over the 615. So I punch that in. Second square root. I'm going to hide my key press under history there, so I got some more room here. 0.682 times 0.318 divided by 1343 plus, notice I don't need any parentheses within my square root there because the order of operations will actually do these correctly on its own. 0.756 times 0.244. The only way you'd need parentheses in here is if you left that as 1 minus. Instead of, I calculated in my head the 0.244. You could do parentheses 1 minus 0.756 if you didn't want to calculate that in your head. Divided by the 615. 0.0215 it looks like. Is our standard error for those proportions. Now I'm sure they'll calculate that for us here in the next couple of slides. P hat, then, if you're going to pool, if you're doing these by hand, pooling is one way to make this a little bit shorter. Pooling them, you can just add, to get the pooled proportion, you add x1 and x2, n1 and n2, and then you divide that out to get the pooled proportion. So then you can do a pooled standard deviation. So for this problem, that would be 916 plus 465 over the 1343 plus, what was it, 615? Yeah, 615. So what is that? 1381 over 1958. We would divide that out to get the pooled proportion. And it should be between the two sample proportions, so 0.705. Notice we had proportions 0.682 and 0.756. 0.705 is kind of like a weighted average. It's closer to the 0.682 because that sample was a lot bigger to begin with. It's twice as big, so we should be closer to the 0.682. Okay, so then next we're looking at now finding the standard error there. So we could either do the standard error the way we did it the first time, or we could use that pooled proportion and use this formula. They should come out to be pretty close to the same. Our test statistic then, like I said, we subtract the two proportions and we divide by that standard error. So what was my proportions again? 0.682 and 756. which is going to be what here? Negative 0.074 it appears to be over that standard error. Okay, now I've been talked about these assumptions earlier, and here they finally come up. Before we can actually complete the full test here, we have to guarantee these assumptions. I realize I didn't finish the test statistic here, but that's coming up here. We have to make sure these assumptions are met. There are two simple random samples that are independent of each other. And that's true. They were taking it 6 years apart, and we didn't use the first sample to determine anything in the second sample. We completely chose randomly from the population at that time again. So there is no connection between the two samples. Second, each population is at least 20 times larger than the sample. We were not told that information, but we were assuming that it is true. I mean, we're assuming there's more than 20 times 1,300 people that are in the workforce. So, more than 47,000 people in the workforce. The individuals in each sample are divided into two categories. Yeah, they're either they use a computer at work or they don't. And both samples contain at least 10 individuals in each category. Yeah, there's at least, each sample, as you can see, contains at least 10 people that don't use a computer and at least 10 people that do use a computer. In the first sample, there were 900 and some that do use a computer and 400 and some that did not. So we have more than enough to meet that 10 requirement. So then, of course, our process is the same as before. You make the hypotheses, which we've done. The decision, make the level of significance, choose the level of significance. We have not done that yet. That level of significance, of course, determines what p-value we need to meet, or we use it to determine our critical value. Then we do our test statistic. We kind of started doing that. We'll finish that up here in a second. And then use, the p-values based on what our alternative hypothesis is. So let's go and walk through this. So here's the same situation. They checked the assumptions, and yes, we met all those assumptions. We have two independent samples. We're assuming the populations are 20 times larger. And then there's at least 10 in each category, and there are two distinct categories in each population. So our null hypothesis is that they're equal. Our alternative, as we said, since we're saying 2008 would be bigger than 2002, that's saying we have to word it as 2002 here is smaller than 2008. Significance level, okay, they're giving us a significance level of 0.05. Again, that's chosen by the testers to determine how certain, the more certain you want to be, the smaller that significance level needs to be. So if you need to be absolutely certain before you reject the null hypothesis, you might put it at 0.01. If it's not that important, just if there's good evidence, you want to reject it, you might put it down at 0.1, 0.10, which would be a 90%. 0.05 is pretty standard. That's 95% confidence level, equivalent to a 95% confidence test. So 0.05% is saying there's about a 5% chance that we could skew our results just by having an awkward randomly chosen sample. So here's all of our information. They found the pooled proportion here. They used that then to find the test statistic. We subtracted this here as we did. And they divided by that standard error, and they get a test statistic of a negative 3.34. Well, if we were doing a critical value, we would have the critical value to compare that to, but here we're doing a p-value, so we need to find the p-value of that test statistic, negative 3.34. So the alternative hypothesis, remember, determines how we find the p-value. The alternative hypothesis is less than. So that means we're looking at the lower end of the curve here. That negative 3.34 is way down here. We want to find what's the probability of randomly choosing a value less than negative 3.34. So if we're using the calculator or any other normal calculation, we're going to distributions, normal CDF, negative infinity. I'm using the negative 999999 for negative infinity. You may use negative 1 and then second EE99 to a negative 3.34. And then since it's a standard normal, it's going to be this mean of 0 and standard deviation of 1, so I don't even need to enter them. The calculator will assume that. We get 4.189 e to the negative 4 means times 10 to the negative 4 means that decimal has to go 4 spots to the left. So that's 0.00042. That's my p-value. That p-value is extremely low. It is much smaller than the critical value of 0.05, so therefore we are going to reject the hypothesis. So our conclusion is there is sufficient evidence to conclude that more workers use computers now, or the proportion of workers who use computers has increased from 2002 to 2008. Then here's the commands for doing it on the calculator. So let's do that quick. Then we go down here, so I've got the information up. So on the calculator, you would go to Stat, Tests, and you can see it's 2-prop z-test. It's option 6. You go there, and it's going to ask you what's x1. Well, in the first sample, there were 916 who used a computer. N1, the sample size was 1,343. X2, in the second sample, there were 465 that used a computer. And the sample size was 615. The alternative hypothesis was less than, so we choose less than there. And we hit calculate. And there we go, it's the same p-value. 4.3 basically times 10 to the negative 4. So 0.00043. Notice before we had 0.00042, which is really close. Just round off errors is all that is. Remember, our test statistic is rounded to 2 decimal places, so that causes those round off errors. So that's how you would enter it in the calculator. We had the same conclusion then of, because the p-value of 0.0004 is less than the significance level of alpha equals 0.05, we will reject the null hypothesis and conclude that the proportion of workers between the ages of 18 and 50 who use a computer was greater in 2008 than it was in 2002. Critical value method. Well, the critical value method, everything stays the same. Our steps are the same. Make the hypothesis, set our significance level, create the test statistic. Now, instead of doing p-value, we have to define a critical value. The critical value, again, goes off the alternative hypothesis. Since our alternative hypothesis is less than, we're looking on the lower tail of the curve here. And our significance level, 0.05, is the probability of being in that lower tail. We've got to find the value that corresponds to that. So that point there is just at 0.05. So we're going to do second distribution. Inverse normal. Remember, since it's a proportion, we always are using the z distribution, so normal distribution. I'm going to put an inverse normal 0.05, and it's going to give me a negative 1.645. That is the critical value. That's z critical. So our rejection rule is we would reject HO if our test statistic z is, now again, the alternative hypothesis is less than, take that out of the way there. Since the alternative is less than, z, we reject if z is less than that critical value, negative 1.645. So, they're going to give us an example here. Are younger drivers more likely to have accidents in their driveways? Traffic engineers tabulate cars, or types of car accidents by drivers of various age. Out of a total of 82,486 accidents involving drivers age 15 to 24, 4,243 of them, or 5.1%, occur in a driveway. Out of a total of 219,170 accidents involving drivers 25 to 64, 10,701 of them, or 4.9%, occur in a driveway. So, can you conclude that the accidents involving drivers 15 to 24 are more likely to occur in driveways than accidents of those who are 25 to 64. Again, using that 0.05 significance level. Well, so our hypothesis, the null, is that they are equal. P1 looks like we are letting that equal the 25 to 64. P2 would be the 16 to 24. So then our alternative is that the older drivers have fewer accidents, so P1 is less than P2. Significance level we already gave, and we found the critical value, and here they get the same one we do. They got alpha of 1.645, or we're using negative 1.645 because we're rejecting on the lower tail. They calculate their proportion. They're going to pool their proportion. Now to pool their proportions, again, they take the accidents for the younger drivers plus the accidents for the older drivers, and then the total younger drivers and the total older drivers, and they divide that out to get 0.049. Remember, the proportions were 5.1% and 4.9%. Well, let's take it out another. 5.14% for the young drivers, 4.88% for the older drivers. Now that pools to be 4.95. That's a lot closer to the 4.88, but remember, there are a lot more of the older drivers. 10,000 is 2.5 times of what 4,000 is. So it should be closer to that one because it's the larger sample size. So our test statistic, they subtract the proportions. So the 5.1% for the kids minus the, they said the proportions the other way? No, they didn't. And the 0.0488 for the older drivers, divided by that pooled standard error again, they get a test statistic of 2.95. We're calculating this a little backwards. This is a right-tailed test. So they're defining this wrong. This is actually a typo here. This should be, let me cross this out. As I said, well, this is confusing me for a second. This should be that P1 is greater than P2. And what they're saying is P1 is the young drivers, the 16 to 24-year-olds, and P2 is the older drivers. So then, yes, they're saying that the younger drivers have a higher proportion. The proportion of the younger drivers is greater than the proportion for the older drivers. So then the critical value would be a positive. So our critical value would be on the upper tail, up here. So the 0.05 would be here, and what we are looking up is 0.95, which would give us a positive 1.6449 or 1.645. So that's where the confusion was there. That is a typo in our PowerPoint. So here, that's why that becomes positive. That's why it was the 0.051 minus the 0.048. That makes a lot more sense now. And so this is them finding their critical value, the 1.645, just as we did. The test statistics of 2.95 is greater than that. So since this is the alternative here is greater than, then we would reject if Z is greater than our critical value of 1.645. And since it is, 2.95 is greater than 1.645, we will reject. So we reject HO, and we conclude the proportion of accidents in driveways among the younger drivers is greater than the proportion of accidents in driveways for older drivers. Construct confidence intervals for the difference between two proportions. So now we've done all this. The confidence interval is actually fairly simple. The difference is the confidence interval is always going to be involved a critical value for two tails. So we've got P1 and P2, again, are found just as always from the samples. The variances, P1 times 1 minus P1 over N1, just as before. And they combine them by adding them up, so they're going to square root them. So that is the combined variance or standard error between the two, as we saw before. Finding the critical value Z. The difference is when we're doing a confidence interval, remember that confidence interval, let's say it's a 95% interval. I don't know what percentage we're going to use here yet, but that 95% comes out of the middle. So then the 5% would have to be split 2.5% on each end here. So for 95%, this would be 0.025 here and 0.975 here. And you'd find those critical values. And this critical value would be 1.96 if this were a 95% interval. And again, they're showing the 100 times 1 minus alpha is the confidence interval. So it's a 0.05 would be a 95%, or 0.10 would be a 90%. So then a margin of error is found by taking that point estimate for the difference in proportions, which is just, the two sample proportions subtracted, plus or minus that margin of error that we found. So let's do an example. In a study of the effect of air pollution on lung function, a random sample of 50 children living in a community with a high level of ozone pollution had their lung capacities measured. 14 of them had capacities that were below normal for their size. Second random sample of 80 children was drawn from a community with a low level of ozone pollution. 12 of them had lung capacities that were below normal for their size. So construct the 95% confidence interval for the difference between the proportions. Now here, the confidence interval can also be used as a form of hypothesis test. If that confidence interval contains 0, then it's saying that it's possible for there to be no difference. If it doesn't contain 0, then it's saying it's very unlikely that there is no difference. So let's find this confidence interval, and then we'll discuss that in just a second. So here we've got our information. We are going to have to check those conditions again. The at least 10 that are in the sample. The population is 20 times the sample. There are at least 10 in each category within each sample, and so on. So anyway, we do have 2 independent samples. Populations of children are at least 20 times as large as the sample. Yeah, there's a sample of 50, though there's 20 times that would be 1,000. There are at least 1,000 children in the world. And then 80, same thing. There's at least 1,600 children that live in low ozone communities. There's 2 distinct categories. Either they have below normal lung capacity, or they have normal lung capacity. Or normal or better capacity, I should say. And yes, there are at least 10 that have low capacity, and at least 10 that do not have low capacity in each sample. So let's take a look. The assumptions are relevant. So our p hat for sample 1 is 14 out of 50, or 0.28. P hat for sample 2 is 12 out of 80, or 0.15. So our point estimate of the difference, we subtract 0.280 minus 0.150, we get 0.130. Our critical value, since it was a 95% confidence interval, as we found earlier, is the 1.96. Standard error, well, we put in the 0.280 for P1, the 0.150 for P2, and we run it through our formula. Sample size for 1 is 50, sample size for 2 is 80. We get 0.075005. I'd probably just do 0.075 myself there, but anyway. And then our margin of error, you're going to take the critical value, 1.96, times that standard error of 0.075. So that gives us 0.147. So it's plus or minus 0.147 here. So we take our point estimate, the 0.130. We subtract that margin of error of 0.147 to get negative 0.017. Then we take our point estimate of 130 thousandths plus that margin of error of 0.147, which gives us 0.277. So the difference between these proportions here is anywhere from a negative 0.017 to a positive 0.277. We're 95% confidence in that range. Now again, this went from negative to positive, which means 0 is in that range, which is saying if this were a hypothesis test, we're leaving the door open that it's possible that the difference is 0. So we would have to say there is not enough evidence to conclude that there is a difference, or to reject the idea that there is no difference would be the proper way of saying that. But we're not really hypothesis testing here, so we would just say we're 95% confident that the true difference in the population proportions is between negative 0.017 and positive 0.277. And they are saying, since this contains 0, we cannot be sure that the proportions of children are really different. And then using the calculator, our calculator does have a 2-sample, 2-proportion z-test. So let's go ahead and enter this information in there. So we're going to go stats, test, 2-prop, z-test. Z-test, we're going to do 2-prop z intervals, what I want here. Sorry, we're down a ways. One prop z interval, 2-prop z intervals, option B. So our first proportion is for our first sample. 14 of the children had diminished capacity out of 50. So N1 is 50. X2 in the second sample, there were 12 with diminished lung capacity. And then N2, the sample size was 80. Confidence level is 0.95. Calculate. There's our interval, negative 0.017 to positive 0.277. So exactly what we had before. And then just walking you through the process here on the calculator. Getting that interval that we just got. So in this section, we learned how to perform a hypothesis test for the difference between population proportions using both p-value and critical value. And then we made the confidence interval for that difference between population proportions. So I'm going to go ahead and end this recording here, and then we will do another one quick for section 3.